Okay, now we want to derive a really important equation for periodic waves. I always say that this is like the F equals ma for periodic waves. So we're just going to use it a lot. You just can't believe how many times we use this equation. All right, so back in the good old days, velocity equals the change in distance over the change in time. Okay, we're talking about waves, right? So let's just say we're going to choose a very special time. For our time, let's say a period, right? So a period. So the question is, how far does a wave move in one period? Well, wavelength, right? Yeah, wavelength. And that's what it means. Okay? So therefore, but what's 1 over the period? What's 1 over the period? That's frequency. So I can just say this is F lambda. So here's the equation. Velocity equals F lambda. And you memorize it. I mean, really, you just use it so much. And we use it in Physics 106 as well. Just one of those super important equations. And it's simple to derive, you got to admit, you know. Oh, what's that? Didn't I just do that? Yeah. Okay, so there it is, all right? So that's the important equation. See how big I wrote it, right? V equals F lambda. F equals ma for waves. But be careful now, because remember, for a string, all right, what does this imply? This implies if you double the frequency, keep this the same, this would double, right? I mean, that's what it says. However, don't forget, for a string or a thin wire, this is the velocity, right? So don't forget, for a string or for a thin wire, that's the truth, you know. Now, here's something else. Let's talk about light. We'll talk about light in gory detail next semester. So for light, the speed is the speed of light, c, right? Now, look, and this is, so let's do it. So c equals F lambda, which is 3 times 10 to the 8th meters per second. All right, now, this is a constant, right? 3 times 10 to the 8th meters per second. It's a constant, you know. So what does that mean about F lambda, though? Well, if you double F, then lambda has to shrink by a half, right? So in other words, you can have any F and lambda you want as long as the product equals 3 times 10 to the 8th meters per second, okay? Now you say, who cares? Well, if you're in astronomy, you care a lot if you're studying astronomy. So here, this is called the electromagnetic spectrum, or you can think of it as the light spectrum. It just shows you the different types of light. So there's incredible ranges. You know, again, you can have any lambda and every frequency as long as the product equals the speed of light. So look, so here's different types of light. Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio. Look at you can have radio waves greater than, you know, this is 100 meters. You can have them even bigger than that. But look at the little gamma rays, 10 to the minus 12 meters. Just an incredible range, right? So, I mean, here, football field all the way to hydrogen atom, you know. Frequency, look at the frequencies. 10 to the 20, 10 to the 20. You know, 10 to the 6th. Look at the energies. This is in electron volts. 1,000,000 over here, 10 to the minus 8 over here. Really small, right? Okay. Where do you have gamma rays? Radioactive elements. X-rays, X-ray machines, duh, right? You know, so forth and so on, right? Now, something else. So think of just pretend you're an astronomer. Now look, this is the entire light spectrum. This is visible light right here. How much of the entire spectrum is visible light? Small percentage, right? Small percentage. So, you know, if you only have a telescope that can detect visible light, are you seeing everything there is to see? My gosh, no, right? All you're seeing is this little section here. You're missing all of that. You're missing all of that. So you know, many years ago, all people had were, you know, visible light telescopes. And then they figured out how to make radio telescopes and microwave telescopes and infrared telescopes or satellites and UV and X-ray and gamma ray. So now they're learning tons of things that they never dreamed of. So this is really important in astronomy. Here's just a little quick example. So here's a star. This is V for visible. So this is the constellation, right? Constellation, you just see, you know. All right, so whoopee, right? And then you look at it in ultraviolet. Holy smoke, what is all this stuff going on here, right? I mean, what's going on here? Look at it in infrared. Wow, right? So there's just so much more that you can see in other wavelengths. So it's really like it's a revolution in astronomy, making all these telescopes and satellites that can cover the whole range. It's really something. All right, let's do another example. Okay, so here we have a nice wave, right? We want to know the amplitude, frequency, wavelength. Okay, first of all, what kind of wave plot is this? All you should look at is the displacement, like the y. And then what's this? It's time, so it's a history. What can you get from history? You can't get wavelength, right? You can only get period, right? Because it's time, you know? All right, so what's the amplitude? So what's the amplitude look like? Well, you know, 6 centimeters, right? Yeah, by the way, amplitude is from here to here, right? Here to here. So 6 centimeters. All right, 6 centimeters. Frequency. Okay, frequency. Well, frequency is 1 over the period, right? What's the period? Well, I don't know. What's the period? Like from here to here, right? So that's like, right? So what's the period look like? Like 0.6, right? Agree? So, well, let's wait a minute. Why do it easy? Let's do from here to here, right? So 0.2 to 0.8. So this is 0.6 seconds. So the period is 0.6 seconds. 0.6 seconds. But we want the frequency, so it's 1 over that. And I promise you that's 1.667 hertz. Okay, wavelength. Hey, I don't know. Okay, you can't get the wavelength from a history graph, right? Because you have time. However, F equals ma, right? So V equals F lambda. Use it all the time. So therefore, lambda equals V over F. And they had to tell you V, right? You know. So it says waves traveling at 2 meters per second. I don't care the direction. Going at 2 meters per second. So V is 2 meters per second. Okay, what's F? 1.667 hertz, or seconds to inverse. You divide that out and you get 1.2 meters. Okay? So all I'm saying is, you know, when you see a history graph and they say, what's the wavelength? You say, I mean, you can't get it directly from the graph. You have to use this equation. Just no other way. All right, let's talk about sound waves. And we're going to talk much more about this I think it's the next chapter, chapter 16. So this is very important. Ultrasound in hospitals, right? You have a baby, you know, they're going to do an ultrasound. Okay, all right, so here's a sound wave. What's the medium for a sound wave? Air. So if you're in the moon, you couldn't hear each other, right? Unless you had a microphone and all that. Okay, so here it is. So how do you produce a sound wave? You should, if you have a speaker, you should take the cover off it and let's see what it does. All it does is go like this. All right, so here's your, so this is a speaker cone. So the loudspeaker cone moves back and forth, creating regions of higher and lower pressure, compressions or rarefactions. Oh my goodness, all right? So where there's a lot of pressure, where those molecules are being shoved together, it's high pressure, compression. Where the air molecules are pulling apart or being pulled apart, it's low pressure, right? Rarefaction, okay? So see, look, here's a pressure. This is pressure versus position, all right? Normal pressure is just atmospheric pressure. No kidding, right? So when the air molecules are shoved together, high pressure. Where they're pulled apart, low pressure. And look at this is pressure versus x, so we can figure out the wavelength, right? So the sound wave is a pressure wave. That's the important thing. Pressure wave. Compressions are crests. I say maxes. Rarefactions are troughs, mins. Okay, that's all. All right, and again, that's all we're going to do. But boy, we're going to talk about this in gory detail next chapter. This is just a little intro. Okay, let's talk about power and intensity. What's power? So power, we use power a lot. We'll use it in 106. You just use power in a lot of different sciences. Power is just energy transferred over time. That's all. You know, think of if you have if your car can accelerate from 0 to 60 in 2 seconds, right? There's a lot of energy per time. If you have an old piece of junk, like the North Shore junker, you can go to 0 to 60 in a minute, right? So it takes a long time to transfer the energy. So it's low power, right? Look at the units. What's energy? Joule. What's time? Seconds. That's called a watt, right? So the units of power are a watt, and you already know that. Let's say you want to got to get a new light bulb for your study area, and you want to get a really bright light bulb. So you want a lot of joules per second. So what do? You get a high watt light bulb, right? So, Okay, so that's power. And intensity is power over area. Okay? So that would mean watts per meter squared. Yeah, W. Uppercase W, okay? And again, just think of focusing a light beam, just get it really, so it's really, really small, Like, have you ever taken light a match and then have a magnifying glass or something so you can focus that light? So you say, if you can focus the light to a really, really small area, it gets really hot. So I say it's high intensity or something like that. Okay, so this is a picture. It's supposed to be like 2- and 3-dimensional waves. So imagine you have a fish tank and you drop a pebble, then you see these circular waves propagate out, right? So that'd be a 2-dimensional wave. Or let's say you had like a little tiny speaker, a spherical speaker, and you had like sound waves, 3-dimensional sound waves, Okay, but anyway, the important thing here is a point source. So a point source, that means, like, again, like you have a tiny speaker and you have these spherical sound waves, let's just say. So a point source, the intensity is power over area. Now what's the area? What's the area of a sphere? The surface area for a sphere is 4 pi r squared. So you have power over 4 pi r squared. So here's the important thing. The intensity is proportional to 1 over r squared. That's the important thing that you want to remember for a point source. And we're going to talk about that when we talk about radiation and radioactivity and radiation safety and all sorts of things. So that's kind of a big deal. All right, another thing, let's talk about intensities of sound, right? The power over area. So again, look at the units. Watts per meter squared. Okay, so it's point source, right? That's what we're assuming, point source. So you don't consider a rock concert a point source, right? Well, if you're far away, it's a point source, okay? All right, so look at these numbers here. So the threshold of hearing. So this is if you're, young and healthy and everything. So if the intensity is 10 minus 12 watts per meter squared, you can just barely hear it. Okay, if in a quiet room, 10 to minus 9 watts per meter squared. Busy traffic, 10 to minus 5. Rock concert, 1. And then threshold of pain, 10. Okay, now I don't care about the thing I care about is look at the range. This goes from 10 to the minus 12, right? 1 divided by 10 to the 12th, which is really, really small, all the way up to 10. So there's a huge range in numbers, right? So the question is, how do you do it? I mean, how do you mathematically compare something that's so incredibly small to something, like 10? I mean, how do you do it? You know, easily. How do you easily do it? So hopefully you remember from high school or whenever you took algebra, when you have something that covers a huge range like this, logarithms, right? That's why they invented them, logarithms, okay? So they have something called sound intensity level. And this is the definition. Don't memorize it. I mean, I'll give it to you, but you just have to know how to use it. So the sound intensity level, they call beta, I don't know why. Sound intensity level, beta, equals 10 decibels. You've probably heard decibels before, right? Loudness. The rock concert was so many decibels, you know. 10 decibels, that's just a unit, times the log of I, whatever it is, a rock concert or whatever, divided by the threshold. Okay? So that's called the sound intensity level. All right, so I want you to, okay, so what I want you to do, what is the sound intensity level beta for the threshold of pain? Okay? What I want you to do, use the information up here, use the definition, and do the math, because you've got to get used to doing this math. So pause your video and do the math, please. Okay, so I assume that you've already paused and now you're back and you've done it. So let's do it. So beta is 10 decibels times the log. Okay, so we want the threshold of pain. That's 10. So it's 10 watts per meter squared. But we divide it by I0, which is 10 minus 12. 10 minus 12 watts per meter squared. Okay, well, first of all, let's just be lazy. What do you say? We can cancel the units, right? Because a watts per meter squared divided by a watts per meter squared goes away. Now, also, 10 is the same thing as 10 is 10 to the 1 power. Now you've got to use what you learned in algebra. What is 10 to the 1 divided by 10 to the minus 12? Well, you subtract, right? Right? Isn't that what you do? Like, look at x cubed over x squared. That's just x to the 1 power, right? Because it's 3 minus 2. So you subtract exponents. So what's 1 minus a minus 12? So we have 1 minus a minus 12. Well, minus minus is plus, so we get 13. All right? So this is, so it's 10 decibels times the log of 10 to the 13. Okay, now you got to remember logs. This is a log base 10. So log base 10 of 10 to the 13 is just 13. So you get 10 decibels times 13, right? That's what it is. Log, whatever. Log of 10 to the 13 is just 13. So then we just get 130 decibels. So you better know how to do that. All right? So yeah, I wrote it down. You can look at it later on. Just refresh. And that is a good place to stop.